Good morning, everyone. We are talking more about probability today. We were talking about actually theoretical probability the other day. For example, if you roll a die and you want to know what the probability is that you roll a 1. So we've already talked about this probability, theoretical probability already. So we've already talked about that. So your objectives is to be able to find the relative frequency, use probability to predict, and find theoretical probabilities and make predictions. So relative frequency and experimental probability are based on experiments. Okay, remember me talking about planting my garden, and I said every time I plant edamame, which is delicious, 7 out of 29 of my seeds I plant sprout. The experimental probability that the next one I plant will sprout is the same probability as my experiment, which would be 7 out of 29. Another example would be flipping a coin 20 times and recording the results. That's based on an experiment, okay? So if I stood up in front of you and flipped a coin 20 times, would that definitely mean that it would come up tails 10 times? No, it sure wouldn't, because it's based on an experiment. So what we do is we take the probability of whatever event we're doing. It's the number of times the event occurs over the total number of trials. That's how many times we tried it. So for example, my planting my seed and it sprouts 7 out of 29, my probability would have been 7 out of 29. Okay? And remember, we can always write probabilities as fractions, decimals, and as percents. So let's look at the first one. Jolene is playing basketball. She scores 11 out of 15 baskets she shoots. What is the, gotta look for these key words, experimental probability that Jolene will get a basket on her next shot? Well, how many did she get on the first 15? She got 11 out of 15. So what's the experimental probability that she will not get a basket on the next shot? Well, she shot 15 times total and she made 11 of them. So 15 minus 11 would be the probability of it not hitting would be 4 out of 15. Okay, it's all based on this experiment that she did up here. Okay, look at the next one. It says, find the experimental probability. Write your answer as a fraction, decimal, and as a percent. A batter gets 6 hits in 12 times at bat. What is the experimental probability that she will get a hit on the next time at bat? So we want to know probability that she gets a hit. And isn't this what all batting averages are made up of? How many times they've got a hit, they've gotten a hit, or how many times out of how many times they were at bat. So she was 6 out of 12, which we know that reduces to 1/2. This is an easy one. 1/2 is 50%, which is also 0.5. And in the baseball world, softball world, hitting 0.5 is really good. Number 3, a goalie blocks 16 out of 20 shots. What is the experimental probability that he will block the next shot? So we want to know the experimental probability that they're going to get another block. Well, how many did they get when they were figuring it out the first time? 16 blocks out of 20 attempts. We're going to reduce both of these by 4. So that reduces to 4/5. This is one of those common ones. Remember, if we change that out of 10, it's 8 out of 10, which is 0.8, which is then 80%. Remember, we move the decimal to the right 2 places. All right, making a prediction. It rains 2 out of the last days in March. If the trend continues, how many rainy days would you expect in April? Well, if you look at this one, 2 of the last days in March. Well, how many days are in March? January has 31, February has 28, possibly 29 if it's a leap year. March has 31, So if it only rains 2 out of 31 of the days in March, you would also expect that in April, but we know that saying April showers, so that's probably not very accurate, right? Okay, and this is what I was talking about earlier. It says theoretical probabilities, when all the outcomes are equally likely, and that is in your brain what should happen. For example, if you flip a coin, what's the theoretical probability you flip a heads? It's 1 out of 2. There's one head out of 2 sides. So you got to just read the directions here. It says use the bar graph to find the experimental probability. This is your workbook page. We want to know drawing a red. Okay, well, this is drawing marbles. This is times it was drawn. This is the color it was drawn. Okay, we want to know red. Well, how many times was red drawn? Well, it's 6. Out of how many total? Well, you've got to add the 4 that are blue, the 6 that are red, the 4 that are green, the 2 that are yellow, the 3 that are orange, and the 1 that's purple. And you get 20, right? So the probability of drawing a red is 6 out of 20 based on our experiment. And we're not talking about how many are actually in a bag of marbles. We're basing it off of an experiment. So that reduces to, take a 2 out of both of those, and we get 3 out of 10, which is 0.3, which is 30%. What about the experimental probability of drawing an orange? Okay, well, how many were drawn from the chart to the right? 3 out of total 20, right? And we know if we change 3 out of 20 into 100, we'd multiply both by 5, so that would be 0.5, which is also 15%. Okay, drawing not yellow, so we can draw anything but yellow. So probability of not yellow, well, let's see, there are 2 yellows, so that would mean there are 18 of them that were drawn that were not yellow. So 18 out of 20, that reduces to, let's take a 2 out, 9 over 10, which is 0.9, which is also 90%. Number 4, drawing a color with more than 4 letters in its name. More than 4 letters. So it can't be 4. It cannot be blue, cannot be red, and those are the only 2 that it can't be, right? So add these up, and it looks like it's 10. So 10 out of total 20, which is 1/2, 50% or 0.5. Okay, there are 25 students' names in a hat. You choose 5 names. 3 are boys' names and 2 are girls' names. How many of the 25 names would you expect to be boys' names? Well, 3 out of, I'm going to add these girls to it, out of 5, this is boys to all. We want to know how many of the 25 that are in there would you expect to be boys' names. Remember, we've got to be consistent. This is just one way to do it. Multiply these each by 5. So I would predict 15 boys' names. Okay, or you could do 3 over 5 times 25 total over 1. That's 1, that's a 5, and you still get 15. Okay, these are all based on the experiments. If you look at the last problems, it says use the number cube to determine the theoretical probability. That means what in your head should come out to be true on a number cube. Remember, all outcomes on a number cube are equally likely, so you have a choice of 1, 2, 3, 4, 5, or 6. Okay, so probability of rolling a 2. Well, there's only one 2 in there, so 1 out of 6. Probability of rolling a 5 is going to be the same thing. How many 5s are on there? 1 out of 6. Probability of rolling an even number? Well, that could be, what, 2, 4, and 6? How many is that? 3 out of 6, which is 1/2. And then probability of rolling a number greater than 1. Well, that would be 2, 3, 4, 5, or 6. So the probability of it being greater than 1 would be 5 out of 6. All right, I just want to ask you, what do you call a number that just can't keep still? What do you call a number that just can't keep still? A Roman numeral. A Roman numeral. You guys know what Roman numerals are? Like 1 is like this, 2, this is 5. These are Roman numerals. But what do you call a number that just can't keep still? A Roman numeral. Oh, goodness. Have a great day.